Welcome back to section 6.1, Solutions and Electrolytes. In this section, we'll be looking at how a solution is formed. We'll look at a solution at the particulate level and look at the thermochemistry behind making a solution, as well as what makes a solution an electrolyte or a non-electrolyte. In order to make a solution, you must have a solute and a solvent. The solute is what gets dissolved, and the solvent does the dissolving. When the solvent is water, the process of making a solution is called hydration. In order for a solution to form, both the solute and the solvent need to have their intermolecular forces holding them together separated from one another. This requires energy, and this is an endothermic process. After the solute and the solvent have broken their forces and have separated and spread out, they can now intermingle with one another, create new intermolecular forces, which will then release energy, being an exothermic process. As mentioned in the earlier slide, the intermolecular forces holding the solvent and the solute together individually must separate. This requires energy and our endothermic processes. When the solute and the solvent have separated and they're allowed to blend into one another, the particles will release energy. It'll be an exothermic process as those new bonds are being formed. If we were to calculate the heat of the solution, we're going to add the enthalpy of the two endothermic processes plus the exothermic process. If when added together, the heat of the solution is zero or negative in value, we would say that is a favorable situation and the solution will form. However, if you added all three of those pieces together and you end up getting a heat of solution that is positive, then the solution would not form. It would be an unfavorable set of conditions. Let's look at making a solution from a different perspective. We know that both the water and the salt seen in this picture have intermolecular forces. If the intermolecular forces between the solvent, which is water, and the salt are stronger than just the intermolecular forces between the ions themselves, the water molecules will have the ability to carry the ions away, as seen at the beginning of this scenario. Notice that the negative ions are being carried off by the hydrogen of the water, and that's because the hydrogen is the partially positive portion of the polar water molecule. Notice the negative region, which is the oxygen of the polar water molecule, is carrying off the cation. Water molecules will continue to carry off the ions, thus dissolving them into the water until no more water molecules are left over to carry on the process. Remember that when ions are floating around in water, they are called an electrolyte. Notice that the solution in the picture has turned on the light bulb. There are lots of positive and negative ions floating around in this solution that carry that process. Molecular or covalent compounds dissolve in solvents very similarly to ionic compounds in water. The only difference is that the polar sugar molecule will not split apart into ions. Notice once again that the positive regions of the water molecules are surrounding the negative end of the polar sugar molecule, whereas the negative region of the polar water molecules are surrounding the positive region of the sugar, which is also polar. In this example, molecules do not break apart into ions, thus there will not be any free floating charges in the solvent. That means the solution cannot conduct electricity, and it is an example of a non-electrolyte. In the picture below, the sugar has dissolved into the water, but it did not break apart into charged particles, so it will not conduct electricity. Take a few minutes to look through this chart to understand the difference between an electrolyte and a non-electrolyte. The only difference between a strong and a weak electrolyte would be the degree of ionization. Strong electrolytes will have almost all ions separated from the compound and dissolved into water, whereas weak electrolytes, only a few ions will actually separate from the compound and dissolve in the water. Generally, strong electrolytes are soluble ionic compounds, strong acids and bases. Weak electrolytes would be insoluble ionic compounds, and weak acids and bases. And our non-electrolytes are going to be our covalent compounds. The only exception to that would be acids and bases, which we have talked about over here on the electrolyte side. Ionization reactions show us the type and the number of ions that break apart when dissolved in a solvent. Let's take a look at the first example. If we cross these numbers back up, you will get the charges of the ions. The subscripts tell you how many you have. So in the first example, iron 2 nitride, we're going to have 3 iron 2 ions and 2 nitride ions. In the second example, we have a polyatomic ion. We're still going to do the same thing. We're going to crisscross the numbers back up, and that's going to tell us we have 1 calcium ion and 2 nitrate ions. Lastly, we'll take the 3 back here. This polyatomic ion does not have a parentheses, which means there's only 1. Cross the 1 back up. That tells us we have 3 sodium ions at +1 and 1 phosphate at -3. One final note, if we were to look at the number of ions that each substance released, we would have a total of 5 in the first example, 3 in the second, and 4 in the third. If they are of all the same concentration, this first substance would be the strongest electrolyte of the bunch. Stay tuned for part 2 of this 6.1 section.